So it's a great honor to introduce Wolfgang Spohn, and pleasure also to touch upon a topic relating to that connects social sciences and also philosophy. In social sciences, our interest is often go beyond where we have, shall we say, measures and metrics. When you have some interaction among agents in a game, for example, when you have made conjectures about the future and so on and so forth. Ranking theory, which Spohn has developed and is a basically a leading proponent of these approaches relating to going beyond, shall we say, probability distributions, metrics, and so on and so forth, and nevertheless being able to derive statements that are useful also for us in the social sciences. So I'm here stressing, shall we say, the applied, the application of Spohn's work and related works. Of course, it's even more interesting to get, shall we say, the pure form.
Okay.
And with these words, I welcome you and looking very much forward to your lecture.
Thank you very much for the introduction. It's my first time in Odense here, and therefore I'm really grateful for the invitation. I hope to bring along nice weather, but it was not nice in Constance when I left, so how can it be nice here when I come here? I hope everybody of you has got the handout. I mean, and it's just the slides which I'm going to present, but so you have something to take away with if you want to. So I hope I had sufficient many copies. Okay. So the whole idea was Timo's in the beginning. He thought I should present my stuff here at this occasion, and I was somewhat unsure about the audience I need, because it was clear to me that you are not philosophers, or only few perhaps, but from all kinds of sciences. But then I also thought, well, you all have a mathematical background, more or less, so that will be a little bit important. I will introduce formal stuff, only basic stuff, but still it's formal. But then I thought, well, that's something you understand, because mathematics, in a way, is the universal language of all the sciences. And so I hope to hit the right level with my talk, but I'm not completely sure. Then Timo has also asked me to give a kind of tutorial afterwards, in the afternoon, after lunch. So everybody is invited to also to attend to that tutorial of ranking theory. And then I thought, well, the other way around would have been better. First the tutorial and then the talk. But now it's this way around. So this talk will be also simply a kind of advertisement of ranking theory. Yeah? So in a way, the introduction into ranking theory itself will be quite brief. And then I want to display what you can do with ranking theory. So as I said, it's also a kind of advertisement. So that's the table of contents. We need not go through all the chapters, so to speak. Yeah? We stop when time is over, then we stop, and we can stop. I mean, I want to get till here. I think we can stop after that or after that, and definitely, probably we don't reach the last section. Anyway, so as an introduction, it's not a talk about social sciences. In a way, it's a talk really about pure epistemology. Yeah? I want to explain to you what epistemology is about. And perhaps, but a good entrance into the topic is that one makes clear to oneself once more that strange mutual inclusion of epistemology and the empirical sciences. On the one hand, you can think, oh, epistemology is one tiny part of the sciences. It's about how our cognition works. And then there are many things in the world which work somehow, and science investigates how they work. So cognition is one of these many parts of the world. On the one hand. On the other hand, it's also the other way around. Epistemology is a very general theory of what we are doing in all the sciences. We are all applied epistemologists when we are doing science. And then we want to know about the general principles about which guide our exploration in whatever field we really inquire. So in a way, epistemology is also a very general theory for all the sciences. Indeed, it is about what we are rationally doing in the sciences. So it is about abstract epistemological principles or models and about their justification, why we ought to follow them. So that makes clear also again that it's a normative theory. It's not about how cognition actually works. It's about how it should work. And then of course we want to be precise in these things. We want to have a precise construction. If we do empirical theorizing, then we get all kinds of problems and it's difficult to get precise. But about the norms, about the normative aspects of epistemology, it's much easier to be precise, and when we can do it, we should do it. And that means that we engage in formal epistemology, using formal methods to do epistemology. Okay, so what could be the tasks of epistemological models which we want to build? Here are 4 abstract desiderata. First, such a model should capture the rational structure of epistemic states at any given time. That's the static part. So think of electrostatics. What's the distribution of electric charge in a body? Yeah? That's the electrostatics. And likewise, what is the epistemic state at any given time? Now, epistemic states change due to many causes, but often due to rational reasons. So such a model should capture the rational change of epistemic states. That's the dynamic part. Like electrostatics, that becomes interesting when we turn to electrodynamics. Such a model should account also for the fact that our beliefs are uncertain and come in degrees. I mean, that's a fundamental observation. Our beliefs are more firm or less firm. They are more certain or less certain, and so on. There are many words for that. They come in degrees. In the meantime, there are many models of uncertainty, and that's very interesting to study. But certainly, probability theory is by far the leading paradigm since 300 years. I mean, it was the first, and that there are alternative conceptions of uncertainty, that's only a very recent discovery. And so the advance of probability theory is about 250 years, and of course, therefore, it's far ahead of all other models. However, all the time we also talk of believing something, of taking something to be true. Not just to be probable, but to be true. That's how we talk. Yeah? We take something to be true, without specification of any degrees. And then we may either neglect this phenomenon, that we also talk of belief simpliciter, as many do, or we may take it seriously, as more and more do in the meantime, fortunately. And this raises the issue of the relation between graded belief and ungraded belief. We seem to talk of both, and the question is, what is the relation? Ranking theory is an epistemological theory that satisfies all 4 desiderata. That's its intention. It's a static and a dynamic theory of belief, simpliciter, or acceptance. That's an alternative word for the same thing. And this is a big advantage over probability theory, which is unable to represent belief.
Sorry,
and that's, yeah,
can I ask you a question? What is the definition of truth?
Huh?
I mean, what is actually
definition of truth?
Yeah, I mean, in a case of, because I mean,
we are really starting philosophy now.
No, I just want to say, I don't want to get into that, but you know, it is a mathematical to prove a truth. I mean, and what actually is the...
No, I'm just using the notion of truth informally. Yeah? And then, of course, we can have the semantic theory of Tarski. Yeah? Snow is white is true if and only if snow is white, and then we can build the theory upon that. Yeah? But it's just
so,
that.
so your truth is an
Let's say the
objective statement.
correspondence theory of truth.
So truth is an objective statement that doesn't depend on whom is going to look at it. Is it correct?
No, I mean, that's the idea. Truth is something objective.
Very good.
But belief in truth is, of course, not objective. That's subjective.
Beliefs are beliefs. Truth is truth.
But but my emphasis is on taking to be true.
Fine.
And that's unqualified by degrees.
I agree,
So far,
I agree.
yeah, that's the point.
I just wanted to understand, what was the baseline? And
Of course, I mean, it's really a big topic, yeah? But we may be satisfied with the correspondence
I'm happy.
theory. Okay. Now, that's something, the first point, is something I could explain for a while. Why isn't probability theory unable to represent belief? Yeah? But just accept it as a claim. I could argue for that one. So the point is, ranking theory is a static theory of belief. That's the first thing. But the dynamics of belief can only be stated by also introducing degrees of belief, as we shall see. So it is at the same time a theory of degrees of belief and explains the relation between belief and degrees of belief. And now, if one looks at things more closely, one finds that the dynamics and the degrees of belief are closely related to inductive inference and to defeasible reasoning, also abductive inference, all these things. So we apply in the sciences all these kinds of reasoning. So ranking theory delivers also an account of all these latter things. And then these are in the end the important applications, as we shall see a little bit later on. So, as I say here, these basic features have widely ramifying consequences, as I'm going to explain. So let us first see what the theory really is. And here's the definition of the theory. So first, we have to assume that we are talking about some subject matter which we can describe with sentences. Or as in a different terminology, there are various possibilities described by language. We consider only a limited space of possibilities. And we call that the possibility space, or it's the sample space in probabilistic terms, or what have you. Or a set of possible worlds, as we philosophers say, but that's also confusing with the talk of possible worlds. So we have a possibility space of, let's say, finitely many exclusive possibilities, but altogether exhaustive possibilities. So exactly one of the possibilities must be the true one. Right? And then we have the script A to be a complete algebra of propositions. So each set of possible worlds, so each subset of W is a proposition. That is a truth condition, which is true exactly if and only if the true or the actual world lies in the proposition, is a member of the proposition. Anyway, so that's what you also use for probability theory. You can always think of probability theory. I'm doing, in a way, just the same. And then I say, what's the n? That doesn't mean anything. Kappa is a negative ranking function, as I used to say, for that algebra of propositions. If kappa is a function from the algebra into the natural numbers extended by infinity, such that the following two axioms hold. I'm just introducing the mathematical structure. The sure proposition W gets rank 0. The impossible proposition, the empty set, gets rank infinite. And then we have the crucial law of disjunction. A disjunction, the rank of a disjunction is just the minimum of the rank of the disjuncts. And this entails that either A or non-A or both must get rank 0. That's what I call the law of negation.
Sorry, A and B are elements of
Because
W.
you are A or non-A, that's equal to W, the sure proposition, and that has 0. That means one of these two must
Sorry,
have.
A and B are two propositions in W.
Pardon?
A and B are two propositions in W. Are two
yeah, sure.
elements of W.
Yeah.
I'm getting the math straight.
So, due to this law, the ranking function is determined by its values for the singleton propositions or worlds, and then the rank of a proposition is just the minimum of the ranks of the worlds in the proposition. Okay, and then the A means that at least one world must get rank 0. Otherwise, the sure proposition could have not the minimum at 0. Okay, so that's already the entire theory. You need not learn more in a way. That's the basic theory. And recall of probability theory. You just have the three axioms, and then you develop entire libraries out of these three axioms. in probability theory. What's the interpretation? That's the important thing. Yeah? And then one understands that definition. Yeah? So ranking functions are gradients of disbelief. So you have to think in double negation, so to speak, and that's something a bit difficult. Yeah, but once one is aware of the fact, then it's simple to manage, I think. So that means if kappa of A is larger than 0, that means that A is disbelieved or taken to be false. Yeah, do you think then you think A is false to some degree? Yeah? Kappa of A equals to 0 says that A is not disbelieved and perhaps believed, but that's not guaranteed. It may also be that kappa of A is 0 and kappa of non-A is also 0, and that means you neither believe A nor disbelieve A, and that means you suspend judgment concerning A. And that's of course something very usual. Yeah? I ask you, what's the weather the day after tomorrow, and then you say, I don't know, I have no idea. Yeah? So you have no beliefs, no positive nor negative beliefs about the weather the day after tomorrow. No, that's suspense of judgment. And so finally that means that if non-A is, the kappa of the rank of non-A is larger than 0, that means non-A is believed or taken to be false, and reversely that means that A is believed or taken to be true. So that's the explication of belief within the theory. So that's the interpretation.
Sorry, can I?
And then you can find, it's easy to see that the axioms entail that belief understood in this way is consistent and deductively closed. And these are the two basic rationality assumptions which you find throughout epistemic logic. Yeah? What is belief? It must be consistent. Inconsistent belief is irrational, and it must be deductively closed. If you believe, believe A, and then think A is true, then a deductive consequence of A must be true according to logic, and that is, if you think A is true, you must also think that the consequence is true. So that's deductive closure. And then you, yeah.
So, sorry to repeat.
It's okay.
When people had this, I forgot now the name, but this famous theorem that says that any axiomatic definition of mathematics contains always an energy shape that cannot be proved, like the parallel.
Sure.
Is that consistent with kappa of equal to 0 and non-kappa equal to 0? Is that
that's the standard objection against these rationality postulates that belief should be deductively closed, and then people say, oh, but deductive consequence is not decidable.
Right.
That's the result you are referring to. And so, thank you for the water. But if it's decidable, how can you ask for doing it, knowing it all the time? But first of all, I mean, that refers to not to propositional logic, which is the only one which is assumed here, but only to first order logic, and then and upwards, or more richer logic than first order logic.
But can I just say that your third ranking condition, K of A equal to 0 and not K equal to 0, can be basically exactly this case, where I can prove either it's true or not true.
But as I said, it's only on the propositional level, where you have propositional logic, and then there. Okay, so we can have a long argument about that. Another point is that, but you have the same problem with probability.
Oh, it's simply mathematics.
You have it everywhere.
It's not your problem, it's a general problem of mathematics, axiomatic mathematics.
Okay, one might also define a positive ranking function, which I call beta. And that's simply, I mean, if non-A is disbelieved, then A is believed, so beta expresses ranks of positive belief. And one can also define two-sided ranking functions in this way, which expresses belief and disbelief at once. That is, if tau of A is larger than 0, then A is believed. If it's smaller than 0, A is disbelieved. And if it's equal to 0, you have suspensive judgment. So this may sound to be the most intuitive function, but mathematically, as I say here, these negative ranking functions, which I have defined first, are the theoretically most fruitful version, and we will see why that is the case. And that may also be the reason why people have not discovered that before, yeah? Because they were always thinking in these other terms, and then you cannot, it's difficult to develop, to come up with a theory, and I will explain to you. You can develop it only in these terms, which may at first seem unnatural, but once you develop the theory, you see that it's natural. Okay, so that's the basic interpretation. And now the crucial thing of the whole theory is, I mean, the theory has predecessors, as I'm mentioning here, but the crucial thing is that you can also define conditional ranks and conditional belief. You do not only believe things, propositions, that is taken to be true, but you also take some propositions to be true under certain assumptions. Given A, I believe blah, blah, blah. Given it's nice weather tomorrow, it will be also nice weather the day after tomorrow. I don't know whether it's nice weather tomorrow, but given that, it will be nice weather the day after tomorrow. That's perhaps what I believe. So we have conditional beliefs. And that means also we need to have conditional ranks, if the ranks are to express belief and disbelief. And that's my definition. The rank of B given A is just the rank of A and B minus the rank of A. And as I say, this definition is the crucial advance of ranking theory over its predecessors. You may know the name of Shackle, George Shackle, who has a long time ago developed a theory of the functions of potential surprise. And that was already in the origins go back to the 1939, I think. And then he has a nice book in 1961 where he developed the theory, but it's all very tentative and it's not very clear. When you look at the functions, they look exactly the same as these ranking functions. But he does not have the, or not exactly the same, but roughly the same. I mean, the law of disjunction, that's something he has as well, and the law of negation, but he does not have that definition of conditional ranks. He has a different one, and then he can't develop a good theory. And likewise, another key word is Cohen's Baconian probability. He has also developed a kind of theory, but as I said, none of the predecessors had that definition, and that's the crucial thing. In other words, that means the definition of conditional ranks is equivalent to what I call the law of conjunction. What's your disbelief in A and B? And there I say, well, that's the disbelief in A plus the disbelief in B given A. And that's quite intuitive. Yeah? What is your degree of disbelief in A and B? Well, one way for A and B to be false is that A is false. So that's its first the degree of disbelief in A. Yeah? But so this contributes kappa of A to that degree. However, given A is true, B must be false in order for A and B to be false. So, and this adds the degree of belief in B given A, disbelief in B given A. And just an aside, we might as well axiomatize ranking theory by this definition of conditional ranks and what I call the conditional law of negation. That kappa B of given A is 0 or kappa of non-B given A is 0. And that simply means conditional consistency. Yeah? Given A, you cannot both disbelieve B and non-B, or believe, positively believe B and non-B. Then is given A, you must not believe a contradiction. So the only assumption built into the theory is that definition of conditional ranks and that conditional consistency. Not only actually you must be consistent, but given any condition you must not be inconsistent as well. And then, like in probability theory, you can go on defining, but I'm not pursuing that now, conditional dependence and independence of propositions. That is then epistemic dependence and independence, but if you recall probability theory, there independence and dependence are crucial notions again, which I can copy here as well. And with the conditional ranks, as you can imagine, I'm able to state a dynamics of ranking functions, and thus also a dynamics of belief. So how do ranking functions learn? That is, how are they updated by new information? Well, information usually does not come with an absolute certainty, but only with some firmness, n. Yeah? So it makes a difference whether you read something in the yellow press or whether you read something in a serious paper, or when you get the information from the original informant. So these are three different ways to get the same information, but in three different degrees of certainty. So we have that firmness parameter. Yeah? And then, well, we need not go into the details of that formula. The idea is simply that if you receive information A with firmness n, then the ranks of n improve by n, and the of A improve by n, and the ranks of non-A go down. Yeah? So the parts of A and non-A, they shift relative to each other just by exactly n ranks. That's the firmness of the parameter. And the further idea is that you keep fixed the conditional ranks given A and given non-A. As I describe it here a little bit. So as I said, we need not study the formula. What's interesting about it now, we can state a complete rule of how to change our ranking functions, and that means also how to change beliefs. And you couldn't do, and the further point is, which I want to explain in the tutorial a bit more extensively, is you couldn't do it with simpler means. You need to have these degrees, these ranks, in order to be able to state such a rule.
Sorry, can I? So this
and just,
little n.
That rule is the ranking analog to a version of probabilistic conditionalization, which is generalized Jeffrey conditionalization, as it is called, and it may be generalized to more complex informational input consisting of some arbitrary ranking function on some arbitrary subalgebra. The important point perhaps for you, because you also had Peter Janfors here giving a talk, this rule also comprises as special cases the expansions, revisions, and contractions, the three doxastic changes dealt with in belief revision theory. However, and that's the point, revisions and contractions are not iterable and hence do not provide a complete dynamics of belief. You do not want only to be able to describe one change, one step of change, but a complete dynamics must describe arbitrary many changes. The point is, you can apply that rule. First you learn about A, next time you learn about A prime, next time you learn about A double prime, and so on. And you can always apply this rule, whereas the belief chain theory of belief revision theory explains only one step and doesn't know how to deal with the second step. And that was that's why I came to think of ranking theory, because I observed this deficiency of belief revision theory and thought about it, what can we do, and then I came up with ranking theory. That was a long time ago, 35 years ago, when I was thinking about these things for the first time. And therefore, ranking theory offers a complete dynamics of belief. The question, of course, was, where do the numbers come from? Yeah? I mean, I'm supposing, so to speak, a mental state which is measured by numbers. How are they arbitrary, the numbers? Where do they come from? And for that reason, later on I've come up with a measurement theory for the ranks. They can be measured. Think of utility theory, which is perhaps the more familiar example. Where do the utilities come from? The numbers. And then people have theorems. Oh, you certainly have preferences. And when your preferences are such and such, then your utility numbers are determined by your preferences uniquely. That is not really uniquely, but up to an interval scale. They are determined on an interval scale. And then, okay, and that explains the numbers in utility theory. And likewise here. But the measurement theory works in a different way. It's here in the red sentence. The point is, if you are a belief contraction, what is a belief contraction? They are simply ask you to give up your belief. Yeah? Maybe you believe that it will rain tomorrow. Now I ask you, no, that's not sure. Maybe it's not raining tomorrow. Yeah? I don't promise you that it won't rain tomorrow, but it's not clear whether it will rain. So then I ask you to give up your belief that it will be raining tomorrow, yeah? Without not substituting it by another belief, or just to give up your old belief. That's a belief contraction. Yeah? And then I can ask you to do these 2 times. First, please contract your belief in A. Yeah? Okay, now we have done so. And then I ask you, well, now please also contract your belief and give up your belief in B as well. Yeah? And then you believe still less. Yeah? Okay. And that has to satisfy certain laws. And if it does satisfy certain laws, these iterated contractions, twofold iterated contractions, determine your ranking function uniquely up to a constant factor. But that's that's a complicated theorem. Yeah? It's quite involved, but it holds, and it explains where the numbers come from. Yeah? Your contraction behavior determines those figures. Yeah?
Can I ask a question?
But it means that belief is only measured on a ratio scale. Yeah? That's a funny thing. And that you all have, you are aware of the problem of interpersonal comparison of utility. So how do I compare your utilities and mine? It's difficult. What's your unit and what's your zero? And my unit, mine zero. And likewise with belief. And that's a problem which has not been fathomed at all so far. Yeah?
That was Chris' question.
I'm just wondering, when I'm listening to this, how does this relate to weight of evidence? Weight of evidence.
The weight of evidence. Do you mean that parameter?
I mean in
When
general.
I say, this one, that n.
I mean in general.
When I say,
sort of the theory
it's
developed by Turing and.
That's a complicated question, let's say. There are various theories about the weights of evidence. One thing is the Webster-Schaeffer theory, which claims to identify the weight of evidence directly. Yeah? And then the Bayesians in probability theory, they say, well, we have another, we don't have the weight of evidence, but we can express this in a different way. I would prefer that answer in this respective ranking theory as well. So you may have little evidence about the die, yeah? And then you have the equal distribution of 1/6 for all the results of the die without evidence whatsoever, let's say. Yeah? And then you have a lot of evidence, really are quite certain that the die is fair. Again, you have the same distribution. Yeah? And then now the critics say, but that must be 2 different epistemic states. In the first case, you have no idea about the die. And it's the principle of insufficient reason that you apply for the equal distribution. And in the other case, you have a lot of information. It's a lot of weight of evidence. It's still arrive at the same thing. So where's the distinction? And the Bayesians say the distinction is, once you have learned very much, it's very hard to change that. Yeah? Whereas when you have learned nothing, then you may easily learn that the die is unfair, yeah, and then you have a different distribution. So, and you can represent that difference in probabilistic terms. That would be the Bayesian answer to the weight of evidence problem, and I would have the same answer here.
Sorry, can I? So you were also mentioning utility theory, right? I mean, David Kahneman. He actually makes a point that utility theory has a problem associated with the fact that it doesn't really know the baseline. In other words, if I'm very, very rich, for me, my utility is different than for somebody which is equal, much, much poorer than me in terms of what is my perception of utility. Would that apply here too? In terms of beliefs?
That's, his criticism is a different one. I mean, he says that you don't really form expected utilities, but really your weighing is a different one from taking the mathematical expectation. That is, you either overestimate or underestimate the small probabilities and such things. But then the standard theory doesn't apply. And
No, I see your point, and you want to
let's
find
say,
a way to kind of normalize.
so far, that theory is just a theory from the rational point of view.
Right.
How it applies psychologically, that would be a matter of empirical investigation. And at the moment, it's just starting to get applied in psychology, in cognitive psychology. Yeah? But the results are still very, very sparse. And then, it would still be an open question. Well, how does the theory of rationality, the normative theory of rationality, relate to the empirical findings? And can the empirical findings somehow refute the normative theory? That's a very complicated issue.
Sorry, from a mathematical standpoint, your W, your set, is an algebra, is a group, or what it is?
No, it's the W and the DA is an algebra.
In algebra,
Yeah.
okay.
But that's just a standard Boolean algebra.
Very good.
And I wouldn't know how, and I haven't thought about it, about
Infinite
extending it to different kinds of algebras.
Okay. Is it infinite algebra?
In
Or?
probability theory, you also, you have the standard thing about normal Boolean algebras, but then in physics you also have different kinds of algebras,
Yes.
and
No, but this
but
one
that's,
probably.
I hadn't thought about that. So perhaps I should explain that because that's important. So you may have recognized that already. There's an obvious pervasive analogy between probability and ranking theory. Simply replace the sum of probabilities by the minimum. Think of the law of disjunction. Yeah? That's the additivity principle in probabilistic terms, which is the basic axioms of probability theory. I replace the sum of probabilities by the minimum of ranks, and the product and quotient of probabilities by the sum and the difference of ranks. Think of my definition of conditional ranks and compare that with the definition of conditional probabilities. That's precisely that replacement of product and quotient of probabilities by the sum and difference of ranks. And thereby each probabilistic theorem is almost guaranteed to turn into a ranking theorem. Right? So now you have that huge development of probability theory, and you can translate almost all of that into ranking theory. Yeah? And I've done that, I mean, in my thick book, I've done that to a very far extent. So why does that work? I mean, the reason is that one might formally understand ranks as order of magnitudes of probabilities. That is logarithms of, now it becomes a bit complicated, of non-standard probabilities relative to an infinitesimal base. Only then you can translate the minimum, the sum of probabilities into the minimum of ranks. But rather only the standard part, and that entails some subtle but important difference. But well, these are mathematical details, but basically that's the explanation why that translation works. But I would like to, this has far-reaching consequences. Mathematically, you can copy large parts of probability theory. And what I'm going to explain, and if I have time, in the rest of the talk, is doing some parts of that. Philosophically, it means you can transfer many virtues of Bayesianism, which acquire a new significance due to the interpretation of ranking theory as a theory of belief. And for the same reason, you may find new virtues. This might suggest that ranking theory is nothing but an extension of the Bayesian point of view. So it's the same, isn't it? However, I think this would be a misunderstanding, because Bayesianism simply has no notion of belief, of taking to the truth. And perhaps just look at the following basic alternative. You might say, what is belief in probability theory? That's just probability one. Okay, and then you have the same properties as in ranking theory. But recall first, note that you cannot change probability one. So once a thing has probability one, it will keep probability one all the time. However you change your probabilities. So you cannot change beliefs in that account of belief. So that's bad. And phenomenally, it's inadequate. If you have probability one for a thing, you can bet your life on that. Nothing happens. So you offer me a bet, I give you 1,000. If I win, I get $1,000. If I lose, you may kill me. And if I'm at probability 1 that I will win, then I can accept the offer. Yeah? But that's not what you do with your usual beliefs. Right? There are many beliefs, but they are still uncertain. Yeah? Now, the other idea is to say, okay, so belief is just probability, say 0.9, or 0.95. That's vague, whatever it is, some threshold. Yeah? But then the fundamental fact is A can have a higher probability than 0.9, B can have higher probability than 0.9, but A and B can have probability lower than 0.9. You can find many examples. And if you take long conjunctions, that will happen. Yeah? I mean, if A1 to A100 have all probability higher than 0.9, the conjunction A1 and A100 will have probability below 0.9, or very small probability even. And that contradicts deductive closure of beliefs. If you believe A and believe B, of course you believe, if you think A is true and B is true, of course you think that A and B is true as well. That's pure logic, isn't it? So in that account, probability theory cannot account for the deductive closure. Now some people say that's a good reason to give up deductive closure. And others say, no, that's the reason why probability theory cannot account for belief. And as I say, I want to have that. Ranking theory is a theory of belief, and that is an important advantage over Bayesianism. Now you have to tell me when I have to stop. So there's a rich literature on that lottery paradox, which I've just explained, and on the relation between belief and probability. Nothing is really satisfactory. I conclude belief and probability are like oil and water. They don't mix easily. Their coexistence and their relation are profound and disturbing issues which become all the more pressing once we have an equally elaborated theory of belief. If you just have a pure notion of belief and a fully developed theory of probability, then you can say, okay, the rich theory is the nice thing. But if you have rich theories on both sides, then you cannot have that attitude anymore. So I think ranking theory should be seen as an independent theory despite its formal similarities. And in the following, if I have time, I shall briefly sketch some applications of ranking theory in philosophy of science only, though there are many other applications as well. Perhaps a nice thing, and there's time for that, Bayes' theorem for ranks. All of you know Bayes' theorem in probability theory and how it's fundamental for scientific inference. Now we have exactly the same setup here. Let A1 to AN be n pairwise and disjoint, jointly exhaustive propositions or hypotheses, and B some other proposition, the evidence. In this setting we may understand kappa of AK as the prior rank or implausibility of the hypothesis AK. Kappa B given AK as the rank or the unexpectedness, the likelihood of the evidence given the hypothesis AK. And then K of AK, kappa of AK given B as the posterior rank or implausibility of AK, the posterior, after evidence B has been collected. And then we have the simple theorem that the posterior assessment of the hypothesis is just that unexpectedness of the evidence given the hypothesis and the prior implausibility of the hypothesis, minus a normalizing factor, that this one. And that very much looks like Bayes' theorem in probability theory, and that's how it looks for ranks. And where we can specify that normalizing factor according to the formula of the total probability or the formula of the total rank. Bayes' theorem for ranks roughly says that the posterior implausibility of some hypothesis is just its prior implausibility plus the unexpectedness of the evidence. And then you have the same mechanism as you are used to from Bayes' theorem in probability theory. It has often been observed that the original Bayes' theorem appears to be the core of abduction or inference to the best explanation. This has also been contested on various grounds. The basic point in that criticism seems to me that the inference to the best explanation is mostly applied to cases displaying no probabilistic nature at all. The one famous thing is always the explanation of the deviation in the trajectory of Uranus due to the existence of Neptune. And there we have the inference to the best explanation to the existence of Neptune. But whereas probability theory involved there, no probabilistic assessment of the hypothesis or whatever. Yeah? So that's why people are also reluctant to say, oh, inference to the best explanation is just Bayes' theorem. So my alternative proposal is that Bayes' theorem for ranks provides the core of inference to the best explanation. And the probabilistic Bayes' theorem is moreover plagued by the problem of the so-called catch-all hypothesis. So you may have, you have the hypothesis A1 to A10, but that's not exhaustive, or and therefore you say, you postulate the catch-all hypothesis, or some other hypothesis applies, and then your set of hypotheses is exhaustive. But what's the likelihood of given that catch-all hypothesis? No idea. What's the likelihood of the evidence given some other hypothesis applies? That's undefined. On the one hand, it's undefined. On the other hand, it's part of the formula of Bayes' theorem. You need to know what the likelihood of the evidence is given the catch-all hypothesis, and that was a serious problem for the Bayesians, and in my view, it's unsolved. It's neglected, so to speak. The ranking version is not plagued by this problem because the formula of the total rank, that was this one, that shows that the normalizing factor is not influenced at all by very implausible hypothesis AI. So the catch-all hypothesis, that's the last resort. That's the last thing we think of, but maybe we get into the situation we have to take it seriously, but initially we don't take it seriously. That is, its rank, its negative rank is very high, or very low, let's say, and then it doesn't influence that minimum at all. So you can really, in ranking theory, you can forget about the catch-all hypothesis, even and it's theoretically okay to do it, though, unlike in the Bayesian case. And that's what I call the innocence of the worst explanation. And I find that a nice argument. No, but you do have to tell me when I have to stop. Yes, because you want to have questions and maybe have questions. And I can, in a way, I can go on forever.
I sense
600 pages of my book that will take days and weeks.
Okay. So thanks for that. So let's round it up in like 5 minutes and take 1 or 2 questions.
Okay,
That would be...
okay, so you mean I should go on for another 5 minutes? Or
if you wish, or is this a good point to...
That might be...
drag it off.
The last chapter, that's a more difficult one. That's a... Wait a minute. That's this one. That's perhaps a nice slide. I mentioned we have the notion of a conditional rank. Therefore, we have a notion of dependence and independence, and we have also conditional notions of that, conditional dependence and conditional independence. And now you may be familiar with the theory of Bayes nets, which has a big career in the last, well, I mean, the really big book which initiated the whole thing, that was the book by Pearl in 1988, 29 years ago. That for the first time presented the theory of Bayes nets with graphical methods. Although in a way, I should mention, I mean, and that whole theory is based on the properties of conditional probabilistic independence. That's the crucial thing. And then once you have these laws, then you can develop the whole theory. But these laws are they are in effect already in my dissertation, the probabilistic laws. And then I thought about ranking theory after parallelism, and that means that you can also have the same theory of Bayes net in terms of ranking theory. the ranking nets, so to speak. And so formally that was the very same. So it's not related to statistics. That's not so clear because the base nets, that they are related to observed relative frequencies. And the question might be, what is the analog in ranking theory? It's certainly not relative frequencies. It's still concerning the theory, it's the very same. What I explained then on the next slides is perhaps just that. That basenet theorizing is crucial for causal theorizing. I mean, there's always the old problem, what is the relation between causation and correlation? And statisticians only find correlation. So how can they draw causal conclusions? And the theory of basenets is the most elaborated answer to that, how you can draw causal conclusions from correlational data. And in ranking theory, it's just the same. You have now the corresponding theory of ranking nets, and that gives you not a theory of probabilistic causation, but a theory of deterministic causation, which is in a way the historically much older topic than probabilistic causation. You have probabilistic causation perhaps since 50 years or 100 years perhaps at most. Whereas deterministic causation from the ancient time, people are thinking about deterministic causation. So what's the theory of that? And that's not clear. I mean, there are old theories. They are all insufficient. There is now the counterfactual theory, and then you have to go into counterfactuals. What's their logic? And my claim is you can do that better in terms of ranking theory. So it's right. But that's slide, the previous slide, and this slide suggests at least that you can really do that. And that was the other aim why I originally thought of ranking theory. Because I observed, I mean, there were sophisticated theories of probabilistic causation in the 70s already, and unsophisticated theories of deterministic causation. And then I was thinking about, how can I raise the, in principle, more important theory of deterministic causation to the same level of sophistication as the probabilistic theories. And that was the other big motive, besides solving the problem of iterative belief revision, of my original development of ranking theory. And that's perhaps a good end point of my talk. So that was the other big thing. I haven't explained how that works, but that's at least the promise that it can do that. Okay, thank you very much for your attention.
Yeah, we have time for a few questions. There's already one.
Yeah, well, I have a rather pedestrian question to begin with, I guess. So your law of contradiction.
Yeah.
I'm a bit confused with the way you set it up. So you say that kappa of A must be 0 or kappa of not A must be 0. Would that being an exclusive or, right?
No, inclusive.
Inclusive.
Or both.
Or both. Okay, that's perfect.
Yeah. I mean,
but
as I said here,
yes. Okay. That took
we
care
can
of.
have both, and that represents suspension of judgment.
Yeah, exactly. So okay. So I understood it right. That was my first confusion. But then I have something more substantial. So on slide 10, this idea of firmness, I guess that translates into reliability or something. With 0 being maximum.
So you take the source of information as more or less reliable.
Yeah, but I can't quite look through this notation right now. But doesn't this entail? This gets you into problem with Condorcet, for instance. With Condorcet's theorem, that should. So you should take into account evidence even if it's produced by a source less reliable than yourself.
Than myself.
Yeah.
But you, I don't know about the weather tomorrow at all, because I haven't read any weather forecasts. Now I'm asking you, I don't know whether you are reliable or not. Maybe you are unreliable, but still you know more than I do, because you do have read apparently the weather report. So I weakly believe you. yeah, so no.
Well, as I read this first, it seems like that if you take your own reliability to be higher than the reliability of the source, right?
Yeah.
Your own reliability swamps the importance of the source, given this definition of M. Okay, and what
that's my own reliability. That's simply my epistemic state, my ranking function. I have a, let's say I disbelieve in A. Yeah? I think A is false. Yeah?
Yeah.
Now somebody comes along and informs me and tells me no, A is the case. And then it's a question of course, then I have to weigh so that my former disbelief with that new information, yeah? And maybe that information only moves me to weaken my disbelief. Yeah? So I don't give up my disbelief. Yeah? I mean, so there's some positive information about A, okay, but slightly suspicious. So maybe I don't give up my disbelief in A, but still I weaken my disbelief in A. That may happen as well.
And how does that figure in the formula? So you meet somebody slightly less reliable than yourself?
Let's say I have rank 10 for it's sunny tomorrow. Yeah? It really doesn't mean right. So I have a strong disbelief that it will be sunny tomorrow.
Yeah.
Now you tell me, oh, the weather report. Now you tell me the weather report says it will be sunny tomorrow. That's what you tell me.
Yeah.
And then I stare at you incredulously and
Sure.
think, is that really true? But still, if you say so, that at least weakens my disbelief in that it will be sunny tomorrow. Yeah? So that is, perhaps it's not 10 anymore, but it's only 5.
Yeah, that's how it should be, but how
Yeah,
does the formula
that's how
work?
it expresses here. Yeah.
Okay.
So my disbelief, so to speak, my belief in A, yeah, or that is my disbelief in A. Sorry, my disbelief in A weakens by 5 ranks, and that's precisely that N. Yeah. So. Yeah. Look, if you take A, what's your degree of belief in A itself, yeah, and what you get in front of? Take B equals A, yeah? Then it's that's 0 and that's infinite. Yeah? Yeah. Okay, no, we should do it on paper, yeah. But I can promise you, yeah, we should do it on paper, yeah. But then I can or on the blackboard, then I can explain it to you. So that's one possible effect, yeah, that I have a strong disbelief in that it will be sunny tomorrow, and after your information I only have a weak disbelief. Still disbelieve it, I can't believe that it will be nice weather tomorrow, but it's less strong after you have said so, yeah, that it will be nice.
There's another question here.
So did I understand correctly that your ranking function gives numbers that are natural and not real?
You can do it also with real numbers. Yeah? The question is, I mean, in probability theory, you have finite additivity. Yeah? And then in the more advanced probability theory, you have sigma additivity. Yeah? If you have infinitely large algebras, then you are thinking also about these terms. Then you have sigma additivity. And likewise, you may think about how to extend that on the infinite case. But that's not, now it's getting more involved in a way. And I have an argument then that minimativity should also apply to infinite disjunctions. Yeah? So
my question
the rank of the infinite disjunctions is the minimum of the ranks of the infinitely many disjuncts. So not the infimum, the minimum. Yeah? That's the difference. The minimum, and that means every infinite collection of ranks has to have a minimum. That is, the range of ranks, the ranking functions should be well ordered. And then the natural numbers are natural choice, and the real numbers don't work in an interesting way.
But don't you have a problem then if you have a set of models that depend, where the only difference is a parameter that has a real value? Because then you can't, then your ranking function will not be a continuous function of that parameter. And that,
I mean, if you really, if you accept that law, and really say you stick to the minimum in the infinite case, and not to the infimum, which is weaker, not to the infimum, and then you get problems to get together the ranking theory with continuum mathematics. Let's say, that's a complicated relation which is not clear to me. But I haven't thought it through. I mean, you might say, well, then we take the infimum instead of the minimum, and then you get a compatibility with the continuum mathematics. But I confess I haven't thought about it. What else then really happens? So, of course, that's a good question.
Can I ask a question?
Last question now.
Okay. So probability theory deals with the events that are to a large extent objective, let's say, or we can agree on the definition of an event, but your theory deals with beliefs. So how can we actually communicate each other about something which is actually very subjective? So
that's true. That's also.
And then also, I mean, let's say the second part of the question is: does your theory requires, an additional theory of how this system of beliefs are created, for example, or are changed dynamically?
I would like to doubt in a way the presupposition of your question. I mean, okay, we all have the notion of objective probability, but what we really have there is very unclear. What is objective probability? We seem to understand it, but really when we start looking at it more intensely, we see we don't really understand it. What that really is. We have the notion of relative frequency, and that's completely objective. But how does relative frequency relate to objective probability? That's already a big issue. Objective probability is not relative frequency in the limit. Because, so we can have a long argument about that. Well, it's not really clear, but still we seem to understand that objective probability. I grant that, and somehow we should make sense of that. And therefore it's a good question, what might be the objective counterpart of these ranks. And that's really a deep question. For instance, causation. I explain causal relation to a ranking theory, and that means relative to the epistemic state. Now, and that seems like causation is just in the eye of the beholder. It's not an objective fact out there, it's in the eye of the beholder, and that sounds crazy. Now I have good precedent. David Hume said the same. It's in the eye of the beholder. So if David Hume says so, I might say so as well. But perhaps David Hume shouldn't have said so. That's unclear. So what I try to add is also a theory of objectification. So to some extent, I can make sense of the notion of objective ranking functions. But that's a complicated thing. It's only chapter 15 of my big book, and sometimes I get the impression nobody has read up to chapter 15. So far I've really no comments on that. I really would like to know what people think about that objectivization theory, but so far I don't know. But as I said, you are right, it's a big problem, and I should say something about it, and I've tried to say something about it. Whether that's acceptable is an open issue.
Okay, thanks. Thank you so much, and this cannot be eaten. No. Thank you. And
but this can be put into this. No, it's a T-shirt. That's.
Very good.
When I lecture now in Constance, I should wear this T-shirt
That would
for
be
advertisement of the D-IAS.
of course. Of course, we are saying.
Nothing comes for
And
free.
it's my son.
I would believe in it.